Here's another couple of example problems. So this problem is a 100 kilogram drum on a storage cradle. And the vertical edge of the storage cradle is tilted at 10 degrees, and this edge is tilted at 20 degrees. This is the free body diagram of this. And so we've got the drum, we have its mass center, so its weight is 100 kilograms times 9.81 is 981 newtons. There's a normal here at B and a normal here at A. And what I do is I kind of sketch across here, and then FB is normal to that, and that's 20 degrees from vertical. And then I sketch kind of a tangent here, and then I draw FA perpendicular to that, and that's 10 degrees from horizontal. Notice that this is not a point. This is a drum with defined dimensions. But once you draw your free body diagram, you can see that the line of action of FA goes through the center. The line of action of FB goes through the center. And of course, the weight acts through the center. And so there are three forces acting on this drum, and all three forces act through this point. So this is a concurrent force system. It's not a particle per se. It's got real dimensions to it. But the forces that act on this body all intersect at a point, and so I can still use particle equilibrium to solve this problem. So we're going to sum forces in the x direction is equal to 0. So the x component of FA is FA cosine 10 minus the x component of FB, which is FB sine 20. There's no other force in the x direction, so that's equal to 0. The vertical direction, I've got FA sine 10 plus FB cosine 20 minus 981 is equal to 0. And so you can set up this matrix. Cosine 10 is 0.9848. Sine 20 is 0.342. Sine 10 is 0.1737. And cosine 20 is 0.9397. So you can enter this into your TI Inspire Simult function. You can use the templates. You can use the command line, whatever. I just already showed you how to do that. And so basically you get FA is 340.7 newtons and FB is 981 newtons there. And so you have to pretty much solve a little 2x2 to get that. Another example problem, some particle equilibrium problems will have a strut on them in addition to a cable. And so remember, a cable only can produce tension. A strut can push or pull. So if you look at this problem isn't solvable until you draw a free body diagram, just like all of these. And so you're looking around, how do I draw a free body diagram of this guy? But if you isolate A and draw just a picture of A, and you draw the weight downward, which is 120 times 9.81, which is 1177 newtons, acting downward. And so then it's pretty clear that TAC is going to have to act up and away from here. And of course, it's at 25 degrees. And so it has to have a vertical Y component that's equal to this guy. So once you draw TAC going this way, then it's pretty clear that FB is going to have to push on the, remember, this is a pin. And so there's a pin there. If you look at the cross-section of that member, there's a big hole there, right there. And there's a pin that acts in that hole. And you can pull that pin out. And that's the guy that we're drawing, that's this guy right here. That's who we're drawing the free body diagram of. And something like that. So we're drawing the free body of that pin. And F of B is going to have to push on that pin to counteract the left-acting X component of TAC. So if we sum forces in the Y, if we write the X equation, we won't be able to solve for anything because there's two unknowns in the X equation. But if I sum the Y equation first, then and set that equal to 0, take up to be positive, I have TAC sine 25 minus 1177 is equal to 0. And you could solve for TAC is equal to 2.79 kilonewtons. And of course, because it's pulling on the pin, then I denote that as being tension. If I sum forces in the X direction on the pin, I've got FAB acting to the right, and that's positive, minus TAC cosine 25, and there's no other X component, set that equal to 0. And you can solve for FAB is 2.52 kilonewtons. And because it's pushing on the pin, that means the pin is pushing on it. So if we're going to split this apart again like we did earlier, the strut is pushing on the pin, which means the pin is pushing on the strut. And so it makes it clear that this guy is in compression. And when you're pushing on a pin or pin pushing on, pushing is compression. This guy's pulling, and so pulling is tension. One other thing I'll show you about this guy is that we're assuming that this horizontal strut only produces a single force on this pin. That is true if this strut is hinged at B. In other words, if it's free to rotate at B. If this guy's free to rotate, then the only force he can develop out here is to push. And we'll see this in a couple chapters when we get to rigid body equilibrium. We will call this guy a two-force member. Which I want to explain why that is now. Well, one of the reasons it's called a two-force is that we're assuming that this guy's massless. So in other words, there's no weight acting here. We're assuming that that weight is 0. So it's free to rotate here, and its weight is 0. And that there's only forces that act at this pin and at this end here. And with those assumptions, then we can say that this guy only pushes on the pin, and the pin only pushes on him. If this guy had a fixed support here at B, in other words, if you had a wall here, and you had this strut coming out, and he was fixed here, there's not a pin, but he was rigid there. If he was rigid there, then you can hang this weight from this guy, and you would not need the cable at all. And so the fixed member would develop an upward force here and could hold this weight up without the cable. So in this case, adding the cable would be a redundant support. In other words, it's not needed for equilibrium. And if you have redundant supports, then the problem becomes statically indeterminate, and that becomes a problem. So I'm just pointing that out to you, that we're assuming that this guy is just a pin here and he's massless, and you'll appreciate that more later. But I just want you to understand that. So this is this problem.